Section 3-8 is on the derivative of sine and cosine. The objective of this section is to derive the trig rules for the derivative of sine and cosine. If you recall in section 3.7, we talked about those. It actually was introduced in 3.6, but we proved, I guess, graphically what the derivatives of sine and cosine are, and we're going to take an algebraic approach now to prove those. And then it says also to find the derivative of sinusoidal functions in real-world problems. So we'll look at some real-world phenomena that can be represented with a sinusoid. A sinusoid is just simply a transformation of sine or cosine, and then use a little bit of calculus on that function to evaluate different things, different rates. All right, so let's take a look at a special limit property that we need to work with first. We'll show you the property here and just talk about it, and we'll also look graphically and numerically on the calculator why this limit property is the way it is. But we'll look further at this in the second half of this section here. So here's the property that you need to know. Turns out that the limit as x goes to 0 of sine of x divided by x is equal to 1. Now again, we're going to take a look at this both numerically as well as graphically to help illustrate why that's the case. But we'll deal more with the formal algebraic proof of this in the second half. So let's flip over to our calculator. And in y1, let's put in the function sine of x over x. And I'm going to set my window up here. We'll go from -10 to 10 for our x's, and we'll go from -4 to 4 should be fine for our y's. We're saying the limit's 1, so this should give us a decent sketch of that graph. And if we graph this thing, here's that graph, and you can see that as we approach the x value of 0, that is, as we're getting closer and closer to that y-axis, you can see that the function from the left side and the right side appears to cross the y-axis there, or approach a value of 1. Okay, so graphically it looks like the limit is 1, as we stated it is. You can also do this numerically by using your table. And let me just start out my table at 0. And I'll make a really, really small change in my table, like 0.01. And I'm just going to go to the table and just have it generate a list of values here. I'll kind of scroll back here a little bit so you can see the values that we're approaching from both the left and the right side of 0. But I can see that we're at 0.99985, and then it's 93 as the last digits, and then 98 and so forth. So it looks like we're getting closer and closer to 1 from the left side. And you can see it's the exact same values from the right side. It looks like we're approaching a value of 1. Of course, we're undefined at 0 because of the fact that you'd be dividing by 0 there when x is 0. But it appears as though the limit is 1 then. Okay, so there's a graphical and a numerical approach to explaining why the limit of this is 1, but we'll look at the algebraic proof of it in the second half. All right. That brings us to then the derivative of sine. Now again, we looked both at both sine and cosine back in section 3.6 and analyzed their derivatives numerically using that nderiv command on our calculator. And it appeared that when we started out with f of x equals sine of x, that the derivative, f prime, turned out to be cosine. The graph looked like cosine. We graphed the cosine function along with it. They appeared to be right on top. Cosine appeared to be right on top of that numerical derivative, so it looked like that was the derivative function. We're going to go through and actually prove algebraically here that that, in fact, is the derivative. All right, so as we've seen with a lot of these theorems or properties that we're working with, that one thing that we are doing when we do a direct proof is we start out by stating the condition or the hypothesis of that theorem. So we're going to say let f of x equal the sine of x. All right, and the conclusion of this is to prove what f prime is equal to. So let's just start out with the definition of what f prime of x is equal to. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. And as we've seen many times now, the first step of this is to replace function f with what it's equal to. So I have the limit as h goes to 0 Now f of x plus h, that says take your function f and replace each of the x's in there with x plus h. So this is going to be the sine of x plus h minus the sine of x. And that's all divided by h. Now, algebraically, there's nothing more I can do with this in the form that it's in. Sine of x plus h minus sine of x, there's nothing I can do to simplify that any further. I need a property, or a trig identity is really what I need, that tells me how I can rewrite this. And we had several properties, several trig identities that you learned back in pre-calculus. And in this case, we have one that tells us how to take the difference of two signs. I have the sine of one quantity minus the sine of another quantity. Rewrite that difference as a product. Okay, and if you've forgotten these, they are actually in the back of your book. In fact, I'll make a note of that here for you, that your trig identities are in the back of your book. They're actually on page 659. If you want to flip back there to see those, you can. But the one that we're going to use is stated something like this. It's the sine of A minus the sine of B. Again, it's the difference of two signs. Sine of one quantity, so for us the A is representing x plus h and the B is representing the x. Turns out that that's equal to 2 cosine of 1/2 of A plus B times the sine of 1/2 A minus B. So that's the property that we need, that we're gonna use here. Okay, so going back to, I'm just gonna draw an arrow here to indicate we're gonna continue on from where we left off there. This is just kind of a little side note here for us, that we're gonna use that little property here. All right, so this is equal to the limit as h goes to 0. Again, sine of x plus h minus sine of x, I'm gonna replace it with what we just wrote down here. It's 2 cosine of 1/2 A plus B. Now A again is the x plus h, and the B is the x, times the sine of 1/2 A minus B. Again, A is the x plus h, and B is the x. And that's all divided by h. All right, so the next step of this is to do a little bit of simplification with that numerator there. So I'm going to write it as 2 times the cosine of, I'm going to simplify what I'm taking the cosine of. I can see that I've got 1/2 of this quantity, and that quantity has x plus h plus x. So there's actually 2 x's in there, but I'm taking half of that whole thing. So half of 2x would just give me an x, and then I have an h, but again, I'm taking half of that h, so I'm going to write that as h over 2. You can write it as 1/2 h if you want to write it that way, same thing. And then for sine, let's do the same thing here. Again, I've got an x plus h minus x. So the x's there cancel out actually. So all I'm left with actually is 1/2 of h. I'll write that as h over 2. And we will divide that all by h. Now, what I want to do is factor out of that numerator. I want to factor out the cosine function. We'll see some nice things are going to happen here as I do that. What kind of leads me to that is the fact that I know I'm trying to prove the derivative of this is equal to cosine. So that's what's going to try to help me lead me to that fact that I want to pull out cosine to get it by itself, and then hopefully I can get rid of the rest of the stuff that's there. So I'm going to write this as the cosine of x plus h over 2 times, and then I have 2 sine of h over 2 divided by h is what's left there. Now what I want to do is, I could have done this in that same step, but I'm going to separate this just so you can see what's happening here. What I want to do is focus on this little 2 here that I've got, that I'm multiplying the sine by, and I want to rewrite that. So it's the limit as h goes to 0, the cosine function stays the same, and that 2 I'm going to change its location here, multiplying by 2, which is how I've got it written here, 2 times the sine of h over 2. Multiplying by sine is the same as dividing by its reciprocal, dividing by 1/2. So I can rewrite this as the sine of h over 2 divided by h over 2. Multiplying by 2 is the same as dividing by 2. So all we did is move that 2 to the denominator. But you can see now I have the sign of one quantity, h over 2, divided by that same quantity. All right. Now what I see I have here is the limit of a product of two things, the product of this cosine times that sine over h. So let's use our property for limits that says the limit of a product is equal to the product of the limits. So this is the limit as h goes to 0 of the cosine of x plus h over 2 times the limit as h goes to 0 of the sine of h over 2 all over h over 2. Limit of a product is equal to the product of the limits. And actually we're ready to evaluate these two limits just in the form they're in now. If I let h go to 0, just using substitution, I'll have a cosine of x plus 0 over 2, of course, which 0 over 2 is just 0. So there's where the cosine of x is going to show up. The second part of this, I'm letting h go to 0, and I have the sine of some quantity, h over 2, that's heading to 0. So that's basically heading to sine of 0. Divided by 0 over 2, that's heading to 0. So I have a limit that ends up in the form of sine of 0 over 0. And if you go back to that very first limit we talked about at the beginning of this section, that's the same limit. And so it turned out that limit was equal to 1. That's the reason why we had to talk about that limit to start off with. So to rewrite this then, this just becomes the cosine of x. And that's what we're trying to prove. Prove that the derivative of sine is equal to cosine. We've done it. All right. That's only half the work, though, of course, because I also need to prove that the derivative of cosine is equal to the opposite of sine. This says if f of x is equal to cosine of x, then f prime of x is equal to the opposite of sine of x. All right, and we're going to go through and prove this one. Now, to prove this, we could go through basically the same steps we just went through for proving what the derivative of sine was equal to. That's a little bit tedious, a little bit of extra work there that we don't necessarily have to do in this case, though. Because one method that we can use to prove something is if I've already proven one property, I can use that to help me prove another property. So we've already proven that the derivative of sine is cosine. We've done that. And I think I can use that to help me prove the derivative of cosine is the opposite of sine, to prove this property. So let's write down what we're starting with. F of x is equal to the cosine of x. And in order for me to use that property, I have to somehow rewrite cosine as a function of sine instead. Well, again, if you flip to the back of your book there and look through those trig properties, you'll find some properties called the cofunction properties. And the cofunction property for cosine of x turns out is equal to the sine of pi over 2 minus x. Okay, now this comes from what are called complementary angles for the two non-right angles of a right triangle. Turns out that this property is true. Okay, so I'm able to rewrite cosine in terms of sine. And if you look at what I have here now, I've actually got a composite function. The whole thing is a composite function. And I know how to find the derivative of composite functions. That's chain rule. The outside function is sine, which we just went through and proved what the derivative of sine is. The inside function is a linear function. And we know how to take the derivative of linear functions, so we are all set. I can take the derivative of the function written in this form. So let's use the rules that we already have in place to find that derivative. So follow chain rule. Chain rule says it's a three-step process here, remember. Take the derivative of the outside function. Derivative of sine is cosine. And I like using those parentheses as a placeholder here as I take this derivative. So first step, take the derivative of sine, which is cosine. The second step is to substitute in or evaluate, however you want to say that, at the inside function. So inside those parentheses, we put the pi over 2 minus x. That's the second step of chain rule. The third step then is to multiply by the derivative of the inside. So pi over 2, that's just a constant, so its derivative, of course, is 0, minus the derivative of x. Derivative of x is 1. So we end up with, when we rewrite this, I'm going to take that negative 1 and put it out front. We'll have a negative cosine of pi over 2 minus x, which isn't quite what we were trying to prove. We were trying to prove that it's equal to the opposite of the sine of x. But again, if you go back to those cofunction properties, similar to the cofunction property we started with, turns out that the cosine of pi over 2 minus x is equal to the sine of x. So this is equal to the opposite of the sine of x then. And that is what we're trying to prove. So with the use of that cofunction property, and then using the derivative of sine that we've already proven, we can actually prove what the derivative of cosine is equal to. And we'll do this many times there. We'll use a previously proven theorem to help us prove a new theorem or find a new property.